Hi, we're just going to finish off our rates of change section with the last question that I forgot to pop up. So here it is, the cockroach question. Okay, so you've got it on your sheet, we're talking about Maitland. So it's the one from the textbook, we've just changed it slightly. So a cockroach plague hit the suburb of Maitland last year, but was gradually brought under control. The council estimated that the cockroach population P, which is in millions, and it's calculated monthly, so T is months, and we started calculating it from January the 1st. It was given by this equation here. So P is equal to 7 plus 6T minus T squared. So we've got a population, and we've got time in months. Population's in millions, our time is in months. So this one is a lot easier than the last question that we looked at with our rates of change because we're given a function to deal with in this case. Part A says to differentiate to find the rate of change dp/dt of the cockroach population. So remembering with our rates of change, right at the start I talked about we were always looking previously at y's and dy dx's. Now the same rules apply, we just happen to have a function of p and its relation is with t. So when we're differentiating p with respect to t. Same rules as we did before. So when we're differentiating this, same rules as before, dp/dt is 6 minus 2t. So fairly straightforward. And that's our first step. Part B, find the cockroach population on the 1st of January and the rate at which the population was increasing at this time. So the 1st of January happened at time equals 0. Okay, so time equals 0 is what we want to work out. So let's have a look at what that is. So I've got to fix it up here for us. Okay, so the question wants two things for part B. It says we want to have a look at the population and the rate at which the population was increasing. So first of all, let's do the population on the 1st of Jan. So when time is 0, that's the 1st of Jan, our population is going to be 7 plus 6, lots of 0, minus 0 squared, which is 7, and that's in million. So initially, when we've started recording on the 1st of Jan, our population is 7 million. The second part of the question says, and the rate at which the population was increasing at this time. So what we're finding then is dp/dt when t is equal to 0. So I'm just popping 0 straight into my dp/dt. That gives me 6 minus nothing, which is 6. So my rate is 6 million, and we're in millions on the top, months on the bottom. So 6 million per month. And underneath it's written, the population was increasing at a rate of 6 million cockroaches per month. So straightforward, I think those two are pretty good. Okay, C. Find the cockroach population on the 1st of April and the rate at which the population was increasing at this time. So we started at January. If we go up to April, we're going February, March, April. So we're looking at time is equal to 3 in this case. Time is 3 on the 1st of April. We're going to pop that into our equation. So P is going to be 7 plus 6 lots of 3 minus 3 squared. And we're going to end up with 16 million cockroaches on the 1st of April. Okay, what it also wanted us to find out at t equals 3 was dp/dt. So what the rate was at that same time on the 1st of April. So what I'm doing is popping in my t value into the dp/dt equation. I end up with 6 minus 2 times 3, which is 0. So that is where the population is not increasing at all. That would be, if we were to graph that equation, that would be the stationary point of that equation, and it's got 0 gradient. And that's going to help us out with with D. Part D says, when did the council manage to stop the cockroach population increasing any further? And what was the population then? So that basically is just rehashing what we've done in C. The population stopped increasing on the 1st of April because our dp/dt was equal to 0. So the rate of increase is 0. That's our answer for that one. And what was the population then? The population then was 16 million. So if our rate of increase is 0, which we got for C, that's when it stopped increasing. So we're just rewriting that one out. Part E, have a look at your sheet. E is saying, when were the cockroaches finally eliminated? The cockroaches were finally eliminated means the population is 0. So what we want to do is get our P function, which is this one, and we want to find out when that is equal to 0. So 2 ways to do it. You can either think of it as a mnemonic. If you like to do it that way, you're going to get the same answers as me here. Or you can factorize through by -1, and you're going to end up with this one here. That's probably an easier way. We're going to be multiplying to -6, adding to 7, and we're going to end up with t minus 7, t plus 1 is equal to 0. remembering back to our functions topic, what we do then, we need to set each bracket to 0. So I'm going to set t minus 7 to 0, and I'm going to get t equals 7 as my solution. I'm also going to get t plus 1 set to 0, and I'm going to get t minus 1 as my solution. Now, not both answers. We don't want both answers. We're going to think what's happening. For 1, we can't have a minus 1 for time because we started measuring at time equals 0, which was the 1st of January. So there's going to be no solution for this one. And what we're going to find is that t equals 7 was the time when our population was equal to 0. And if you count through, the population, when the time when that happens, t equals 7, is the 1st of August. So it is counting 7 months along from the 1st of January. Okay, we're nearly there. Let's have a look at F. Now, F wants us to find what was the average rate of increase or decrease from the 1st of January to the 1st of April. Now, the answer is 3 million per month, but let's have a think about how we got that. So we want to have a look at the change in the populations. So we're going to have population at April minus the population at January. Oh, excuse my pen here. Over the amount of time that we've got. So we've got the population at January. Hang on, I'm just going to fix this pen for a second. A bit better. So our population in April was 16 million that we've just already discovered. Our population that we started with in January was 7 million. The months or the time in April was month 3 and the time in January was month 0. So if I take those away, I'm going to get 9 over 3, which is 3, and that's where my 3 million per month came from for F. When I did this in class the other day, a lot of you have said you've done that in science before, so think back to your science lessons and see if that might actually help you out a little bit with that question, if you get a question that's looking like an average rate of increase or decrease. Okay, G. G wants us to draw the graphs of P and dp/dt. So let's have a look at this one. P's very straightforward. It was our quadratic. We factorized it and we got zeros at 7, and we also got a 0 at minus 1. Now, I'm eliminating this part of the graph here up to the 7 because we only started at time equals 0. So I only want from this point onwards on my graph. And we've got our 0. We know midway between minus 1 and 7 is 3. 3 was where we had our stationary point, and that gave us 16 million. So that's enough really for that graph. If we wanted to put our domain and range in, our domain is between 0 and 7 because we don't want less than time being equal to 0. And our population was between 0 and 16 million. Let's have a look at dp/dt. So this was the one I think that you guys will probably struggle with the most. This is a new thing, and you just need to think a little bit. Once you've got your P graph, you can go straight from P to dp/dt. So like with the question we did previously where we just had the function without the equation, when we have that original graph, we can look at what's happening at each point along that graph and transfer that to our rate of change graph. So my vertical axis is going to be dp/dt instead of P, but my horizontal is still going to be T. So I would always like to mark out the same points that I had on my graph for the function for my dp/dt graph. Okay, so let's think about what happened at each of these points. Now the one I'm going to put in first is the 3. The reason I'm going to put into the 3 in there first, because I think that is probably going to be the easiest one to think about. So what happened at 3? Or what is happening at 3 on the graph here? Oops, I'm trying to highlight that for us to see. 3 is a stationary point, isn't it? Okay, so that's telling me that dp/dt is equal to 0. So I'm going to straight away pop that in here. Okay, here that's saying dp/dt is equal to 0. That's a stationary point. Over here, we know the steepest part of our curve is going to have been originally at this point here. Okay, when t was equal to 0, our dp/dt is at a maximum, and that gave us 6. It's decreasing until we get up to the top point here. So again, I put my ruler on in class to find the slope at each point to think about it, but we can actually physically work that out at each point if we like. If you want to work out dp/dt at our point here, if you want to work out dp/dt at various points along here at t equals 1, t equals 2, you're going to find that our values are going to be decreasing. If you want to have a look at that again, if I go back up to the questions that we just worked on, we've worked out a lot of these dp/dt's. So we worked out that here for part B, when time is 0, dp dt was 6. That's the part that's on my graph to start with. So here, at time equals 0, my dp dt was 6. And it happened also that my original population was 7. So let's have a look then and see what else we've found out. So we've popped part C on there as well already, but that was our dp dt was equal to 0 at time is equal to 3. Okay, so that was my middle point here and over here. And what I've just confirmed is my point down here. So I've just thought, well, that's t equals 7. I've got t equals 7 here. That's when our population, if we have a look back here, is eliminated. So that's when our rate of change is over. So I'm going to see what was happening there because I wasn't sure if I was right. So I went back to think, okay, well, let's figure out what dp dt is at t equals 7. So I've just found my dp dt equation here, and I've popped in 7, and I've got 6 minus 14, which is minus 8. So I'm down here at minus 8. I could have tested other points in here if I needed to, but that should be enough to understand that we've gone from 6 through 3, and we're way down here at the bottom point here. But if you need to pop in and test other points in there when you've got a function, you can, and that's something that I think you'll probably find really helpful. So our domain in this case for t is between 0 and 7, and our range for our dp dt is between minus 8 and 6.